Okay. So this question is based on the based on actually several processes. So here you can see they are talking about sulfuric acid production and what are the principles we use and the uses, and first time that they have given you an inorganic conversion. Okay, inorganic conversion. So we normally see there are organic conversion in the paper, so automatically you have organic conversion. This is the first time after, I think, about I would say before 2000. Okay, before 2000 there were questions like having these inorganic conversions, but this is the first time that they have asked for this one, this inorganic conversion, which we typically normally don't see. Okay, so we have a conversion, we have to go from limestone to acetylene, and here from nitrogen to sodium nitrite. Okay, so how do you go this, how do you do this? That is one. And they have asked few simple questions based on sodium carbonate, the Solvay process. So these are very straightforward. The first one and third one is very straightforward, but the second one is a little bit tricky because you need to understand how to approach this. Okay. And in part B, they are asking about the ozone layer depletion. So I think we have discussed the little bit a part of this question before in the previous questions as well. So we will first go through these reactions and processes. Okay. So first one, with the aid of balanced chemical equations, you need to list the steps involved along with the reaction condition in the manufacture of H2SO4 using contact process. Okay. Okay. This question says use balanced chemical equations, and you need to list the steps involved along with the reaction conditions, okay, in the manufacture of H2SO4 using the contact process. So if you have asked this type of question, okay, so student starts to write pages. Okay, for good student, he or she will write like 1 page for this one. Okay, but remember, okay, in the marking scheme, if you consider about the answer, they have only expected the reactions that is involved. They have to list the steps involved, but they have not even considered about them. Okay, only the reaction with the conditions, that's all. Okay, so typically what are the reactions that you normally know when the sulfuric acid production is done? So that is very important to know because there are some reactions that you normally know and some other additional reactions that I can suggest you. Okay, so the typical reaction that is involved in the sulfuric production is you have sulfur solid plus O2 gas, which form SO2 gas. This is typically the first step, and you have to heat this. Okay, and in the second step, you know, we normally use the catalyst, which is reversible in reaction, vanadium pentoxide. And earlier I told you this was replaced with, in fact this is replaced with platinum. So earlier they used platinum, then platinum is replaced with vanadium pentoxide because platinum is more expensive. Okay, so this will form SO3 gas. So you can use vanadium pentoxide, and the atmospheric temperature is 122 atm, and the temperature is 450 degrees Celsius. Okay, so you have SO3. So from sulfur you first form SO2 gas, and from SO2 gas you form SO3, right? And the next reaction is when you have SO3 gas and when you put this into water liquid, so it will form it will form H2SO4. This is the typical reaction. Okay, So when you have SO3 gas, if you dissolve that in water, this will form H2SO4. This one, right? The other thing is in the manufacturing process, we supply SO3 to H2SO4. Okay. In the manufacturing process, which will eventually form H2S2O7. This is called oleum, or we say pyrosulfuric acid. Okay, and when you have this one, we just add this a little bit of water to form 2-sulfuric acid. Okay, so the advantage of just putting H2SO4 to SO3 without putting water is that you have H2SO4 here, right? But the problem here is this reaction is not complete. So SO3 is added with H2SO4, little bit of previously made H2SO4. Then you form oleum, pyrosulfuric acid, and then you add little bit of H2L for this one because it will form 2-sulfuric, which is more beneficial. Okay, so in the industrial process, we don't use this reaction. This is the first one, this is the second one, this is the third one, and this is the fourth one. Okay, in the industrial manufacture. But don't forget, this reaction is also in generally present. Okay, so in industrial process, these are the main 4 reaction. That is one part that you should know. Okay, the second thing is, remember, this sulfur, it is not necessarily to need to which means what I'm going to tell here is you don't need this sulfur at 0 oxidation state. Okay, it can be even -2. Okay, for an example, it can be like PBS, ZNS, and even from H2S. Okay, so anyway, somehow you need to form SO2 from these 3. So the easiest way to form these 3 is you need to combust. So basically, when you use PBS with O2, it will form lead oxide plus SO2. Okay, and you can use zinc sulfide, zinc oxide plus SO2, and you can use H2S, and here SO2 plus water. Basically water plus SO2. So instead of this first reaction, okay, you can write down these reactions as well. So don't forget about that. Because remember, nowadays to find sulfur is easy. Okay, because sulfur is already refined and sulfur is already there. So you just need to combust and get SO2. Okay, but earlier processes like using the platinum ages, so they had these sulfur ores, we say. Okay, so lead sulfates, tinabas, so H2S, so these are sulfide compounds that you can combust with SO2. The problem with this is, you see, you have some additional products like lead oxide and zinc oxide, so it can be a problem for here. Okay, so you have to remove this, but here there is no problem if you use sulfur. So these are the 4 main reactions that you need to know. Other than that, remember, there is this one which we normally don't use in the manufacturing industrial process, so you don't need to write this one. Okay, this is not necessary, only these 4 is enough, and you need to mention the conditions as well. So that is first question. The second question is physiological properties. So that is very important, physiochemical properties. Uh-oh. Okay, so when you have a question like explain the physiochemical properties means they are asking, always remember they are asking explain this condition based on the Le Chatelier's principle and the condition that you have used, how it suits for the reaction. Okay, so remember this particular reaction is reversible and exothermic. Okay, this reaction with sulfur, the first step of the reaction in the contact process is sulfur plus oxygen. No, sorry, it was SO2 plus oxygen. The second step is reversible, which gives me the idea that if this reaction is exothermic, the process on top should be heating and the process below is cooling. Okay, now think about this. You need high amount of SO3, which gives me the idea if this is the heating process, if I cool the system, I'm going to cool. So if I cool the system, the heating process would be happening according to the Le Chatelier's principle. So to get a high amount of SO3, low temperature is good. Okay, to get a high amount of SO3, low temperature is good. Why? Because this reaction is exothermic, which means I'm going to heat externally, but the system like cooling. Okay, so if you cool the system, heating process will happen, favoring more formation of SO3. Okay, so temperature, low temperature is good. But they have used 450 degrees Celsius, which is not low. Why? That is the explanation that you should give. Okay, so first you need to explain according to Le Chatelier's principle, low temperature is good. But they have used 450 degrees Celsius. Why? The reason is if you use low temperature according to Le Chatelier's principle, it is perfect. But the problem is if you use low temperature, the chemical kinetics of this reaction is very slow. The reaction rate is very slow. So it will take a lot of time to convert all SO2 to SO3. So there is a problem here. Okay. So according to Le Chatelier's principle, low temperature is good. But the problem is when you use low temperature, the reaction rate is very minimum. So that they have used an optimum temperature of around 450 Celsius. Okay, so that is one explanation that you should give about the temperature usage. Okay, and the second one. So second one is the pressure. So here you can see there are two molecules and here there is only one molecule. Okay, so if you want to shift from here to here, the Le Chatelier's principle says if you decrease the pressure should increase in the system. And if you increase the pressure should decrease the system. So if you want to get more SO3 in this particular system, if you decrease the pressure, decreasing means you are externally decreasing the pressure, you try to decrease, so the system going to increase. So how to increase? You have to go from 1 mole to 2 mole to increase the pressure, because if the amount of moles is increasing in the system, there will be more collisions, which increases the pressure in return. Okay, that is how it increases the pressure. So here you need SO3, which means from 2 moles to 1 mole, which means the pressure should decrease. So the pressure should decrease means to make that process favoring, you should increase the pressure. Because if you try to increase the pressure, quickly these two moles will react and form one mole so that the pressure is decreased in the system. Okay, so you try to increase the pressure, so the system will move accordingly that to decrease the pressure. So this forward reaction is favoring, so more SO3 is formed, so that according to that pressure should be high, because if you have high pressure, you can see quickly this reaction will happen and make the pressure low. But you can see still they have used 1 to 2 atm. So why is that? Okay, so here they have used 1 to 2 atm. So why is that? The reason is if you use high amount of pressure, okay, there is a disadvantage of cost for this particular process, because giving a high pressure means the system equipment, the cost is very high. So in case if there is a high cost, okay, you cannot go for higher pressures, because we do this process to get some profit, some beneficial. So if you are consuming a lot of money for your equipment rather than using just the normal optimum temperature and pressure conditions, there is a problem. So here in this particular condition, in the particular reaction, you see according to Le Chatelier's principle, low temperature and high pressure is good. But see, theoretically it is very nice. You need to use low temperature and high pressure. But when it comes to practical reasons, you see they have used totally a different situation. So you clearly understand what you learn theoretically is not what you have to do in practice. This goes with everything basically. When you do a research or anything, this goes with everything. Theory is not what you need. You need practice. You need a practical knowledge. You need to think each question practically. Okay, so here according to this situation they have used this one. Why? The reason I explained you. Okay, temperature is low is okay, but they have used high to maintain good reaction kinetic. High pressure is okay, but they have used normal optimum temperature 1 to 2. Why? Because of the cost. Okay, so this is very important reaction that you need to explain, because they are asking about the physiochemical properties. Okay, so I will share. So these are the physiochemical properties that they basically needed. So then give two uses of H2SO4. So very common, very easy. First one, normally everyone knows the fact that H2SO4 is used in battery acids. So in vehicle battery acids, we use H2SO4. That is very important for giving H plus to the system and maintaining this redox reaction in batteries. And the second important usage is we use H2SO for the production of fertilizers, right? Not the normal fertilizers from ammonia like urea. We need like H2SO4 to form superphosphates. Okay, this is a type of fertilizer that we used for good agricultural purposes. That is superphosphate. From phosphate, we use superphosphate. So for that, for the conversion, we normally use sulfuric acid. Okay. So these are two main uses. There are many, but these are two main uses. Okay. And the second one, so this is done basically. So try to know the understanding of the contact process. So this might not be the complete comprehensive knowledge that you necessarily need, but you have the idea now. You know how to form sulfur dioxide. It can be formed from either sulfur or either sulfide ores like lead sulfide, zinc sulfide, or even from the H2S gas. So you need to know that. Then from the main physiochemical properties is the reversible reaction of SO2 with O2, giving SO3. So this is reversible and exothermic, and I explained to you why this condition is used. And remember another thing, so you might think like, why exactly this 180m and 450? Why it is not 400? Because 400 is very close to 450. Why? Because how they determine this pressure condition and temperature is, they will first fix this pressure to a certain value, and where they vary the temperature and see what is the yield here for SO3. Okay, so that is one of the method. Then they try to keep the temperature at a certain constant and change the pressure and see how much is the yield. So for this particular condition, 180m and 450 degrees Celsius, the product yield was like about 98%. So in the particular this reaction, the production yield is 98%, means, which is very good, right? So we don't need to change the temperature or pressure from this. So that is the idea that they had based on this explanation for low temperature and high pressure. They don't need to use that because this is enough, because the percentage yield is okay, right? So if you are using this one and your percentage yield is like, let's say 50%, then automatically either you need to change the entire process, or you need to give low temperature and higher pressure, making the yield more and more. Because if your yield is 50% and you are still using this 1 to 2 ATM and 450 degrees Celsius, there is no use in using this process, because these are not just for laboratory purposes. These are high industrial, large scale processes. So you need to understand that fact. Okay. So, right. So the next question is the inorganic conversion part. This is after a long time. So you have limestone, which is calcium carbonate. So you need to get acetylene, right? But if you remember, if you have limestone, you can first heat this limestone to form calcium oxide and carbon dioxide. And when you have this calcium oxide, what you can do is you can so basically you will have okay, I will just board the decision. Okay, so the idea is you have limestone, so you have to form C2H2 acetylene. Okay, so the first thing that you can do is you can heat this limestone to form calcium oxide and carbon dioxide. Okay, so I am not sure whether this type of questions will be asked in the process, because later they have not asked, but indirectly they can ask in a particular question as a byproduct. Okay. So, then you have calcium oxide. So these are solids and gases. And then you can use calcium oxide with carbon, solid, or even graphite. So this will give calcium carbide plus CO2 gas. And when you add calcium carbide to water, it will give C2H2. Okay. So this reaction is straightforward, because if you remember this C22 minus plus water, if you remember about the anion analysis, what we discussed earlier, C22 minus or either N3 minus, NH2 minus, H minus, P3 minus. All these reacting with water would give gases, right? So we discussed the anions that would give gases with water. So this will give ammonia, and H2 and PH3 phosphine gases. So these are necessarily that you need to know. Okay, you need to know these things. And here there is E2 minus. So if you add water, it will form the acetylene gas. Okay. So this is one of the process that you can do for limestone to convert it into acetylene. There are not much of important points that you can take from these reactions. And the other one is you need to go from N to NaNO2. So this is little bit tricky, right? Because you need to take NaNO2. So this is not easy. But you can imagine if you have NaNO3 and if you heat this one, you will form NaNO2 plus O2. Okay. This is one of the ideas that you can take. So if you have NaNO3, you can take NaNO2 by heating. And then if you have NaNO3, how to take NaNO3? So the easiest way to take NaNO3 is you react this with HNO3 with let's say sodium hydroxide. So if you have sodium hydroxide with HNO3, it will form NaNO3 and water primarily. So the only necessary thing is you need to form HNO3 from N2. So this is what? This is the process of forming HNO3. So you have to just mention the process of forming HNO3 from N2. Okay. So the first thing that is normally going to happen here, so these are important things, right? So you have N2 gas plus H2 gas, which forms ammonia gas. So this is normally the Haber process that we do. And the temperature is 450 degrees Celsius and 200 to 250 atm. That is the pressure. And you can use iron or Al2O3 as your catalyst, and you can use K2O as your catalytic promoter. It is a promoter of a catalyst. So this is called a catalytic promoter. Okay. Then you will have this ammonia. You can balance this. This is the step one. And you need to mention where you can take. So this can be taken from natural gas. And this one, nitrogen and oxygen, remember, normally you take from the fractional distillation. Okay. Then you have ammonia that is going to react with oxygen to form the main component, that is NO. And this reaction is going to happen in 4:5 ratio. Basically, we say like 1:9 when the overall composition is taken. And it will form 4NO and 6H2O in the balance equation. The condition for this is 850 to 1000 degrees Celsius. That is the temperature. And pressure is 1 to 10 atm. And either you can use platinum or rhodium as the catalyst. And here again you can tell O2 is from fractional distillation. Basically fractional distillation. So here you have NO. Then if you have NO, I will write down the other processes very quickly. So it will form NO2. And if you have NO2, O2 plus water, it will form HNO3. Okay. If you just put water with NO2, it will form HNO3. But in addition, it will form NO as well. But if you put NO2 with H2O in the presence of oxygen, it will form HNO3. Okay, if you just put NO2 to H2O, it will form HNO3 plus NO. So this reaction is not much efficient. Why? There is a byproduct which is problematic. But if you use NO2 H2O in the presence of oxygen, then only HNO3 is formed. So if you have HNO3, then the other reactions are very straightforward. You can react with NaOH and then you can form NaNO3 and then you heat NaNO3 to form NaNO2. Okay, so these are straightforward processes. Okay, and in the meantime, where you react this with NaOH to form NaNO3. So you have to mention where NaOH came, right? So this is from the electrolysis of NaCl, aqueous solution of NaCl. This is the caustic soda production. So think about how much industrial processes are involved within these two reactions. You should know contact process, sulfuric. You should know the limestone and the decomposition. That is a part of the, we can say, ion extraction. Okay. Then here we should first know ammonia, then nitric acid. So if you think about the usage of caustic soda, C5. And the next question is based on sodium carbonate, so 6. So this overall questions, it almost covers like 6 industrial parts. Okay, so this is very important. If you are answering an industrial question, you should be able to combine each industrial conversion. Then you will have a comprehensive knowledge and you can imagine when there is a clear indicator chart is given to you. You will see in the following questions, like recently there was 1 or 2 questions that is asked. So you will see how these questions are combined each other. Okay, so this is again a very important reaction. And again, you should be able to like explain this using the physiochemical properties, right? For an example, this reaction is exothermic and minus 92 kilojoule per mole. This Haber process form. Okay, so if this is exothermic, which means the heating, this is cooling. So cooling the system would favor the forming of ammonia, but they have not used a low temperature. This is 450 still. So the same thing goes with the like the SO2 plus O2 reaction. They have used optimum. Okay, but here remember in SO2 plus O2, they have used 450. Here is also 450. But the problem here is when you use here like the for the ammonia production N2 plus H2, the pressure condition, it is 200 to 250, which gives you the idea here they have used a higher pressure. But why? The reason is in there for SO3 production the yield is about 98%. But here the yield is not much if you use the 1 to 2 atm. So they have to go for a higher pressure in this system. Okay, so that is very important to understand. Okay, so this is done. So we have a few more questions. Okay, so this is basically done. Then the next thing is we have some questions based on sodium carbonate. So if you remember, when you want to prepare sodium carbonate, we does not prepare sodium carbonate directly. We first prepare sodium bicarbonate. That is the way. So we just prepare sodium bicarbonate and then we heat to form the sodium carbonate along with the byproduct calcium chloride. Okay, that is the industrial process that you should normally know. So the first question is state the starting materials used in this process. Someone is waiting. Wait. added. Okay, so I'll share again. Right, so this is about sodium carbonate and the Solvay process. So we know typically we don't get sodium carbonate directly. So we come from sodium bicarbonate, then we heat this along with sodium carbonate. Then we get the main product is sodium carbonate when you heat sodium bicarbonate. But instead of having only sodium carbonate, there is a byproduct that is always formed, that is calcium chloride. So remember about that one as well in the process, right? So state the starting materials used. So the starting materials, basically we need three. One is the NaCl brine solution. Okay, that is the brine solution. The second one is we use limestone. Okay, and the third one is we need to use ammonia. So these three are very important because from limestone we need carbon dioxide, so we need ammonia from Haber process, and we need brine from seawater. So these are the how these materials are obtained, right? So we obtain CO2 from limestone, and we obtain ammonia from Haber process. That is the other thing that you need to know. And we need brine from seawater. Okay, so these are the three starting materials. So these three are necessary. That is done. And how obtain? Limestone, Haber process, and seawater. That is done. So give the final byproduct. So I told you there is a byproduct that is formed, that is calcium chloride. So give two reasons why we use, that is a very important thing that you need to necessarily know. Give two reason as to why low temperature are used in this process. So here you see we use this carbon dioxide, right? That is one. And here we need to precipitate out this sodium bicarbonate. That is the second one. So if you use low temperature, it facilitates the dissolving of this carbon dioxide in the solution. That is one. Because at high temperature, it likes to get into the vapor state, right? So first thing is it facilitates the dissolution of carbon dioxide in the solution. That is one. The second thing is when the temperature is lower, again, it facilitates the precipitation of sodium bicarbonate. This is another important thing that you should know in this this typical procedure. Okay. Then uses, so there are many uses like using the bleaching in this soap even, and sodium carbonate typically used in very important case, if I can remember, that is the manufacture of glass. Because when you have only SiO2, the glassy nature does not optimized, but you sometimes add a little bit of sodium carbonate to optimize its nature. And remember, sodium carbonate, if you can remember, we use this as a primary standard as well in the volumetric analysis, if you can remember. Okay. So propose a method to convert the final byproduct. Okay. So final byproduct was calcium chloride. So if you just think about this question, okay, you can understand for this particular question, the reactions that you need to know necessarily need to be, you don't need to remember all these reactions. You need to understand the process, right? Industrial chemistry, please don't by heart. Just try to understand what is happening. And if you understood in that way, automatically the reactions would come to your mind. That is what the normal case. So if you have calcium chloride, you have to convert that into gypsum, which is calcium sulfate dot 2H2O. So first thing is you need to understand what is calcium sulfate dot 2H2O, which is gypsum. And if you have calcium sulfate dot half H2O, we say that is plaster of Paris. Okay. So here we need to have another conversion from this one, and we need to using seawater as natural resource. Okay. So the easiest way is when you have seawater. So you first precipitate out NaCl. So there will be no sodiums that will be available. So if you precipitate NaCl, and in the mother liquor, then you have these sulfates, and when you add this calcium chloride to sulfate, the mother liquor basically, then you will have this gypsum forming. This is very special, especially in we study this especially in the salt process, right? So this is not necessarily important here, but you should know the general idea. That is important here. Okay. And other than this, you know all the reactions that is happening in this particular process, right? That is very important to know. So wait. I will come to that very quickly. So where is it? Okay, so I will share the screen. Right, so this is directly from your resource books. So remember, resource book is not only enough to answer your questions, you always see some lacking part. That is why you come here and understand everything and try to complete everything, right? So you see, this is the entire process that we have here. Okay, you need ammonia, then you need carbon dioxide, and you need the brine. Okay, to precipitate out finally the sodium bicarbonate, and you heat it to form sodium carbonate. Okay, so you see NaCl, so you have sulfate, so you can add the calcium chloride to form the gypsum. So that is a different story. The important thing that I want to tell is this one. Okay, why we use this type of a system, that is very important to understand in the Solvay process. Okay, so this is an efficient process that we use to do this principle, which is called the counter current principle, which means you send one reactant from the top, the other one is coming from the bottom, which is the ammonia. If you send both from the top, there is less time, less interaction between the reactants that is going to happen, that is going to actually react. But according to this counter current principle, which allows the interaction of these reactants efficient, making a good yield. That is the important thing that we use in one tower as well as in another tower as well, because we use normally two towers. Okay, and the other things are very straightforward in this particular reaction. The only necessary thing is when you have calcium oxide along with ammonium chloride in one of the steps, you will have calcium chloride. And when you have NaCl in the limestone, there can be formed calcium chloride. So this is the main byproduct which is formed. Okay. So that's it. So we will go to the last part. That is the ozone layer depletion that we have discussed few parts earlier also. So as an alternative to chlorofluorocarbon, the CFCs, hydrochlorocarbons are also introduced to to reduce. See, to prevent, not prevent, reduce. Because I told you earlier, CFCs are the main pollutant, one of the main pollutant of the ozone layer. And HCFC is okay, but I told you this is still can pollute. That is why we went for HFC without the C things, without the chloro things. Okay. So, however, both these groups compounds not only deplete ozone layer but also contribute to other environmental problems. So, basically, it can even can contribute to global warming as well. So, draw the chemical structures of CFC and HCFC with a single carbon atom and label each of them as a CFC or HCFC. So, if you can remember the structures. Okay, so CFC means chlorofluorocarbon, right? So typically you can this is the general chlorofluorocarbon that we normally draw in the case with a high amount of efficiency. Okay, and you can draw other chlorofluorocarbons by replacing these fluorines with chlorine. Okay, but anyway, remember you can replace this with chlorine, this one, and you can draw another one maybe. Yes, you can draw another one. Yeah, you can draw these three structures, but you cannot draw like with fluorochlorines because it will not then become chlorofluoro. Fluoro is not there. But all these are chlorofluorocarbons. We have chlorines, we have fluorines, and we have carbons with single carbon atom. That is what they expect. Okay, so these are chlorofluorocarbons. So what should be the other one? Hydrochlorofluorocarbon, which means you can imagine from here now there should be hydrogen, chlorine, and fluorine. Okay, so this can be one, and this can be, there can be another one maybe. Yeah, there can be another one like one chlorine, two fluorine, and hydrogen. This can be another one that you can draw, and you can another one like two hydrogen, one fluorine, and one chlorine. The idea is the terms that is explained by the abbreviation like CFC, chlorofluorocarbon, that should be exist in the molecules. Chlorine, fluorine, carbon. Chlorine, fluorine, carbon, and hydrogen. So these different structures can be acceptable. Okay, so if you remember why I told you this before, why they went to HCFC from CFC, even though like, yes, HCFC is still able to destroy ozone, like depletion of the ozone layer, HCFC is still okay to use. Why? If you can remember, I told you this before. Because you use refrigerator here and it goes towards the stratosphere, these chlorofluorocarbons. So CFCs goes here. Okay, and it interacts with UV radiation and it will form chlorine radicals basically, and this will start to react with O3 and deplete. Okay, but the problem with HCFC is still it can go, and react with UV, form chloride radicals, and again it will react with O3 and can harm the ozone. But the difference is for HCFC, the lifetime is very small. Okay, so in the lower atmosphere itself, this HCFC is completely destroyed. It does not go towards the upper stratosphere, but CFC they have a higher lifetime, so they will go towards the upper stratosphere and react with UV radiation to form the chloride radicals, and then it will form the chain reaction destroying O3. So this is one of the ideas that you should know, and I explained to you this before. So we have draw. So under normal atmospheric conditions, CFC are more reactive than CFC. Comment on this. That is, yeah, the primary idea is like the lifetime. That is the what we say. We will say like that a qualitative idea. Okay, that is one of the ideas that you can give. Okay, and the other idea is think about the structures of the compounds. There is one hydrogen in the hydrochlorofluorocarbons. So this hydrogen, this bond is not much strong than the carbon and fluorine bond in CFC. So this bond can be easily broken down. That is why this reaction is very fast even at the lower atmosphere, and that is why they are quickly get destroyed before moving on to the upper stratosphere. Okay, so hydrogen is beneficial here. And name another environmental problem that is associated. Comment on their relative contribution towards this environmental problem. So this is directly comes from the note, because we always try to study this from the note. Because if you think about HCFC and CFCs, both are greenhouse gases which can contribute to global warming, which is the gradual rise in temperature. And as well as the contribution, when you compare the contribution according to the explanation that I gave you, the contribution from HCFC is little bit lower than CFC, because CFC their lifetime is very high, so it can like exist in the atmosphere to a larger extent than HCFC. So contribution from HCFC is higher than HCFC because of the lifetime difference. And the environmental problem is the global warming, which is the gradual rise in temperature. Why? Because these two are greenhouse gases. So you can explain these two are greenhouse gases. So it will affect on the greenhouse effect and cause global warming. And when the contribution is compared, the life you can mention about the lifetime. Okay. So this is done. So you touch little bit of the global warming here, but not much, just a little bit. And identify 3 properties of CFC that make them suitable as a refrigerator. So now we don't use a refrigerator with CFC, you know. So we use like HFAC, if you remember, and we use HFC as well. Okay, which is not ozone layer depletion carrier. Okay. So identify 3 properties why CFC. So normally we use why, because this is mostly inert, chemically inert. That is the important thing that when you use these for refrigerators, right? Because these are typically the cooling agents. So this is inert, and this is with low viscous nature. You can write down the low viscous nature, and they are chemically inert nature. And even you can write down the boiling point. So when the boiling point is very high, so you can write down those 3. Okay, so this is necessarily not important to remember, but in case you need to know, you should know. Okay. So explain how CFC contribute the depletion of the ozone layer. So this is straightforward. I have already explained this to you before. So you just take one of the compounds CFCs from here and you irradiate with UV radiation. Then automatically it will form the chlorine radical. Then this will react with O3 to form ClO plus O2, and O2 also with UV can form two atomic oxygen. So this goes like the continuation. So if I write down the reactions, so we have many reactions. So if I write down, so let's say we have CF3Cl. Okay, that is one of the compound that you can take. So with UV, so it will form CF3 plus Cl, and this Cl can react with O3 to form C. In fact, ClO or Cl radical plus O2. Then oxygen also can react with UV to form two atomic oxygens. Basically, you don't need to either put the radical or this. You can show atomic oxygen, and this atomic oxygen can react with or Cl radical to form Cl radical again and O2. So you can see here the reaction start with here, okay, and ends it here, okay. Which is most dangerous? Why? Because you see the reaction start with forming Cl radical and destroying O3. And in the process which it destroys O3, again another Cl radical is formed, which again can come and participate in the same reaction again and again and again. So you can see this Cl radical here acting as a catalyst, which allows this reaction to happen as a chain mechanism. So this is a chain mechanism that is continuously forming. Okay. So this is why CFC are more dangerous, because all ozone will be gone. But thanks to the other processes where CFCs are destroyed, and thanks to the other process where this O3 to O2 conversion is reversible, where if you have some amount of oxygen in the upper atmosphere, it is again can be converted to O3 as well. So this is in equilibrium in the atmosphere. The problem is when this equilibrium is achieved, there is no problem. The problem is when you have these exposures that is going to atmosphere and destroy ozone, the equilibrium will be broken down because there is no more O3. You see, there is no more O3. It will be a problem. Okay, so that is what they have asked in the latter part of this question. You see, so the contribution, how it contributes, you can write down this reaction and explain chloride radical is formed. This can again participate in the second reaction and do this as a chain mechanism. So this is how it participates. Briefly describing the consequence of the ozone layer, identify 3 problems associated with this. So there are many problems. So we'll have a lot of skin cancers. That is one of the products. And it can cause cataract in eyes. That is another one. And elevates the atmospheric temperature. So this is another one that can happen because there are more UV radiation that can happen. And even there can be some genetical changes in the cells of people, where because of the UV radiation, there can be like genetic disorders that can happen, which causes certain skin cancers. Okay. So there can be skin cancers, temperature increments, and as well as the cataracts in eyes. So these are very few examples. When you go through the book, there will be a lot of, but just identify 2 to 3, that is fine and enough.